Okay, so let's get started. Good morning, everyone. So we're gonna go now to the fourth lecture of the Dark Matter School in Natal, 2023. And in the past lecture, okay, wait. So let me present. I need to, Ricardo, could you connect the charger? Please. Yeah. Okay. Let's see if it's working, charging. Okay, good morning, everyone. So let me present entire screen. Okay, fine. Okay, so let's continue to the fourth lecture. So in the past lecture, I asked you to derive the Boltzmann equation, which was this equation right here. So let me zoom in. Okay, here it is. So where you have the abundance as a function of the freeze-out temperature or freeze-out parameter, xf, which x is the mass over the temperature, and inversely proportional to the dark matter annihilation thermal cross-section. And they're up to some constants, okay? Well, they are not actually constants because the G star S and G stars refers to the relativistic degrees of freedom at a given temperature. So depending on the temperature you're talking about, which is the freeze-out temperature, then Gx, G star, and G star S have some values, which might be different depending on your model. So maybe you have a beyond the center model where you have lots of, relativistic degrees of freedom, then G star will change according to the standard model value, okay? But the one thing that I did not emphasize because I went fast last lecture is that X, we have assumed so far that X is M over temperature, which is around, let's say 20, 30, whatever. However, this is just a result we get from solving fully the Boltzmann equation. The actual function for x is this one that I'm going to show you, and I also asked you to derive, right, as one of the exercises. So Clarissa sent me an email this morning, asked me to write explicitly the list of the exercises that I asked you in the past lectures. So I'm going to do it so you can really know what I'm asking. And I want to emphasize this one. So the freeze-out parameter, or the max over the temperature, is actually a function of the mass of the dark matter particle and also the annihilation cross-section. But there's a, let's say, a log or logarithmic dependence on those mass and cross-section. So it's not precisely m over t. There is an m here dependence, and there is this temperature dependence is somewhere embedded in this formula, okay? But what I'm gonna use today is that x, let's say, depends on the log or ln of the mass. It's proportional. Okay, so depends on the mass. Slightly, but does depend. Okay, so that's what we finished. We finished this one. And we also emphasized that the thermal annihilation cross-section has a S-wave dependence and a P-wave dependence. The S-wave dependence is a term in the annihilation cross-section which does not depend on the velocity. The P-wave term depends on the velocity, okay? That's what distinguishes them. Fine. Is there any questions from the past lecture? No? Okay, so now I'm going to the fourth lecture. I already sent to Clarissa this morning, this lecture notes. Hold on, here it is. So this one I will go slowly because you won't see a lot on textbooks. So there are textbooks on dark matter I think the one that I really mostly use is the one from Stefano Profumo, but it does not go into the details that I'm going to cover today. Okay, so that's why I will go slowly today, because there are some caveats that are hard to grasp if you just read a book, and there are just basically none of them. And most of them are related to very old papers from the 80s, late 80s, early 90s. And the notations were very different than the ones we use today, and they're very long. And so I'm trying to say at the end of the day is that please do pay attention to this, okay? Okay, so we were discussing the dark matter relic density. That's the form. That's annoying. Let me turn off my WhatsApp. Close it. Okay. So we have covered the dark matter relic density under the freeze out regime. Remember, the freeze out is simply a mechanism at which the dark matter stops being in thermal equilibrium when the annihilation rate equals the expansion rate. All right. So the key aspects of this freeze out mechanism was the thermal annihilation cross section, which for now, let's just focus on the Feynman diagram. So that was what we had was chi bar, dark matter, anti-dark matter particles. So a Fermi, anti-Fermi in this diagram, or scalar, anti-scalar, or whatever, vector, anti-vector, annihilating produces something. Can be standard model particles or can be something extra. At the end of the day, what you had was an equilibrium number density that goes like this, the one in red. But because of the expansion rate of the universe, eventually that number density stopped decreasing and froze out. And that's the freeze out mechanism. And what we solved was the Boltzmann equation to find the yield at infinity, where at very late times. And that yield, which was the number density over the temperature, was inversely proportional to the annihilation cross-section and some x, the freeze-out parameter. And the abundance, as you know, omega h squared is rho over rho critical density, which is n times the mass, right? But n, what is n? Well, y is n over s. So once I know the yield, I know the number density. I just multiply by the mass, I get the relic density. So that's why you often see in books, they calling y, the yield, as the abundance. It's not actually the abundance, is basically it is up to some constants, right? So in some books they call, I solved the abundance. Well, it's not the abundance, but okay, fine. It's just a matter of speech. Okay, so the key ingredients we had was, for the whole mechanism, was thermal equilibrium and non-relativistic freeze out. So we assumed that the dark matter, when it froze out, was a cold relic, okay? Was non-relativistic. And now we're gonna cover now some aspects. There are exceptions to this whole abundance calculation, which are called, it's an old paper by Gondolo in the late 90s, okay, 97, if I believe, 97. So it was 3 exceptions to the relic density of cold relics. So that was the title of the paper for 97. So that's what's going to cover that. So the first one is the resonance. So let's assume for now that the mediator between the dark matter particle and the standard model fermion is the Z boson, okay? I'm just assuming it could be Z prime, could be a scalar, whatever. It won't change anything. I'm assuming it's to be the Z boson. Why? Because I already know its mass, so I have one last free parameter in my discussion. Okay, that's why I'm assuming to be the Z boson. We know that its mass is nearly 90 GeV. 90 GeV. Fine. So what happened is the annihilation, not thermal cross-section, the annihilation cross-section is proportional to the S being the S parameter from the Modeston variable, which is S related to the center of mass energy is squared. Mass of the mediator, you can see there, yeah, right. Depends on the mass of the mediator, which is the Z boson, and mass of the mediator squared gamma Z. Why I'm considering this? Because I'm considering at the resonance. At the resonance, I have to take into account the width of the propagator. Fine. So when SS is equal to center of mass energy squared, the center of mass energy in my case is how much energy I have. If dark matter particles are non-relativistic, so let's say their mass is simply their rest mass. So I have m chi here and m chi there, so that the center of mass here, I have 2m chi. So that's the center of mass energy. Therefore, when the Z mass is equal to m chi, when that happens, I have a resonance. So there's a boost in the cross section. Why? Because the denominator, this one below, hold on. This term below, this one, will go to 0, and then this cross section explodes. Okay? So that's called the resonance. That has to do with standard model physics, has nothing to do with dark matter. This always happens. Okay, fine. But look at this. So for the case of dark matter, it's easy that you have m chi. You have m chi here, m chi there. So the center of mass energy is twice m chi. So let's just prove it. So let's say that in the center of mass, I have P1 is momentum of the chi particle. First chi particle has energy E1 and momentum P star. The second particle has energy E2 and momentum, which is minus that momentum at the center of mass, minus P star. So S is equal P1 plus P2 squared, which is a Lorentz invariant term, is equal. So I have I'm in the space, the Minkowski space, where I have the x component, the time component is positive and the x component is negative. That's why I have this term minus here. So I have E1 plus E2 squared minus P1, and then this P2 is the opposite, is squared. This goes to 0. I have E1 plus E2 squared, where what is E1? E1 is the energy of the particle. Well, if I'm assuming it to be non-relativistic, it's simply its mass. So I get m chi here plus m chi there. Everything is squared. So I get 4m chi squared. But S is equal to the center of mass energy squared. So I take the square root of that, I get the 2m chi, which is what we were discussing in the very beginning. Okay, so that's the center of mass energy. Okay. Any questions so far? Okay, so this is, however, this center of mass energy is true for colliders. So if you're here today, so the only thing that matters is the energy of the particle or its mass if it's non-relativistic. But this is not true for an expanding universe. An expanding universe, that is an N here. For an expanding universe, this is not true. Why? Because I have this thermal energy. Okay, and let's compute it. And just to emphasize that today, the velocity of the dark matter particles is roughly 10 to minus 3 C. How do I know this value? So does anyone in this room know this? Why I know that the velocity of the dark matter particle is 10 to minus 3 C? Patricio? So the dark matter particles are moving from that?
Yes, but also the solar system is moving around the galaxy.
So the dark matter particles are moving with a velocity of 10 to minus 3c, corresponding to us?
I would say it is the relative velocity. I think that's what it means.
Yes. So v is the relative velocity. Actually, what it means is the dark matter particles are not moving. They have zero velocity. We are moving. So we are moving towards something which is static with a velocity which is 10 to minus 3c. So the relative velocity between us and the something that's static is 10 to minus 3c. Okay? So there is a fluid which is basically slow moving. Really slow moving, is static. So as far as we know, the galactic halo of dark matter particle has zero angular momentum. So it's not rotating. It's zero. Okay? And then it's rotating zero. And then, but we are moving towards something which is there still. So we are moving with a velocity around the sun with 10 to minus 3c. So in a galaxy cluster, that galaxy in a galaxy cluster has a different velocity corresponding to something which is still static, has a different v. At the sun, there's one v, 10 to minus 3. Far away at the outskirts of our galaxy is a different v, slightly different. But because the sun is actually almost at the outskirts of the galaxy. Okay, so it's nearly 10 kiloparsecs, so we are 8.5 kiloparsecs from the center. So we are already towards the end of the galaxy. That's why we say that the maximum velocity that we can have towards something which is static is the difference between our velocity and the one which is right there in the corner. Okay, the further away I go, okay, the further away I go, for instance, I can infer what is the, for instance, I have something static and you have stars in our galaxy. What is the velocity of the fastest star in our galaxy? That's exactly the maximum relative velocity that dark matter particles can have in our galaxy. Okay, this is just the critical velocity. So what is the velocity at which I make sure that we are still in a bound system? So if dark matter particles or stars have a velocity which is larger than the critical velocity, right? So therefore, then if it is larger, that star will strip out and will no longer be in the bound system. So if we were at the very corner of our galaxy, let's say the velocity would be a bit different. And that would be the mean velocity of the dark matter. Well, the velocity is not constant, but let's say there's a mean velocity of something.
So this velocity is for our galaxy.
Different galaxies have roughly the same. Roughly the same.
It would be about the distance from the center.
That's why you don't have a velocity, you have a distribution of velocity. But I'm going to cover that in a different lecture.
But in this situation, need the velocity of a dark matter population with respect
to us.
Other dark matter population. I mean, for production.
Yeah, for the production, it is. That's why we neglected the velocity. Okay? Sounds good?
Yeah, but for larger systems, this velocity
is larger.
So
it is larger. For galaxy cluster, which have more mass, the velocity is actually 10 to minus 2c. So it's an order of magnitude larger. See? So different objects have different relative velocities. Thermal cross sections.
Every object size, different sizes of thermal cross section.
Yes. And there was a paper was saying the title was really catchy. It was like a selective selection. Dark matter annihilation is very selective. It was something like this: selective dark matter annihilation in the sky. This paper was published in PRL. Was just taking data from gamma rays and place a limit on the dark matter annihilation cross section for different targets. On the thermal one. So take into account that the velocity, so sigma v this V is different for galaxy and for galaxy clusters. So they would get just overlay the limits from galaxies and galaxy clusters.
So, recapping, in this case, in a research perspective, I would have to compute my cross-section normally about this diagram. And then if I have some assumptions about how the universe evolves and how this halo formed, for example, and I want to, for example, put some bounds on my model about infrared detection.
No, I will not cover that now because I'm going to cover just below.
Okay, but anyway, in this case, I would have to just take into account this velocity dependence, and it will change for each case.
Yeah, so the particle physics model doesn't care. Right? It's the same. I'm saying if you want to place a limit, then you have to say, okay, for galaxies, this is the limit. For galaxy clusters, this is the limit. Your particle physics models doesn't care if it's a galaxy or a galaxy cluster. Okay? But look, pay attention. That's sigma. Sigma V's, as I told you, sigma V average has a velocity dependence in some cases. So if in my model there is a velocity dependence on sigma V, then if I use galaxies, let's say it depends on sigma V squared, remember? A plus B V squared. So let's say in my model there is no V dependence, none. So I just take which limit is the largest, give it the most restrictive. This one, I'm gonna take this one. But okay, but mine has a V dependence, my theoretical model. So what I'm gonna do is probably for galaxy clusters where the V is larger, their limits for my model will be more constrained. You see how it is? So it's just particle physics, but you have to know that for galaxy clusters, your limit will be more restrictive.
Yes.
And why I'm saying this? Because at the end of the day, experimentalists, just place a limit. Sigma V average. And you as a theorist, you have to know which one's more relevant for your model. Okay? Because what they do is, I measure some gamma ray flux that depends on some sigma V, whatever is sigma V, over the mass squared. I measure flux. I constrain this ratio. You have to realize that the sigma V is more relevant for galaxy clusters or galaxies. You are the one who has to do it, not them. So this is just to emphasize again that experimental limits, as far as dark matter is concerned, they do depend on the model. When you interpret in terms of sigma V, the flux is the measurement. That's it. You measured. This is model independent. But when you interpret the measurement of number of flux of gamma rays to dark matter annihilation, then you're making an assumption. Okay? So the assumption is there. Just to make sure, for now, you're saying that my experimental limit is model dependent? Yes, it's model dependent. When you interpret in terms of sigma V, I'm not saying what you experimentalists do are model dependent. They are model independent. You measure something. I don't care what model is. But when you try to interpret that flux in terms of sigma V, that is an assumption in that leap. Okay? Any questions?
So, but the dark matter halo, Maxwell-Boltzmann distributed, right? So, does that mean that every individual dark matter particle has a random velocity and you have a tail of bigger velocities?
Yes, there's a velocity, it's a Maxwell-Boltzmann, so it's the same way. So there's a probability of one dark matter particle having one velocity, and there's a probability of another particle having a different velocity.
So the dark matter particles in the halo are moving.
I'm moving in this sense.
In that sense.
In that sense. There's a velocity distribution, yeah.
The homogeneous assumption is that they are still.
Yeah. because they're moving corresponding to us. So I'm just rephrasing. So it's like the dark matter parts had a velocity. We were just stopped looking at them, and they had some velocity. Okay? So that's what it says. For instance, let's say we are in a gas. There's a dark matter particle. So we are moving in this gas. It's not us, just the sun, across the whole galaxy. There's one particle moving corresponding to the other because they are rotating. The whole galaxy is rotating. So it's like they're actually one moving this velocity, the other one is moving this velocity because the whole system is rotating. The stars are rotating where the halo is. And then one comes with a velocity distribution of f of v, which is Boltzmann-like, which has a peak and a tail, right? And the other one also could be at the corner of the tail or at the corner of the bump, right in the bump. So when you have to integrate that as a function of velocity, okay? So when we do compute sigma v, that sigma v is not the precise value of sigma v, because you don't know what v is. Could be v very at the end of the tail, which is almost twice the value, or at the one at the peak, which is 3/2 something. I don't remember. It's 300. So the most likely velocity of a Maxwell-Boltzmann distribution is 300 kilometers per second. 230, I believe, 250, something like this. And the one at the peak would reach nearly 700 kilometers per second. So it could be off by a factor of 2 or 3. Just by this, when you take a limit on sigma v, that limit by itself only could be changed by a factor of 2 or 3. If your sigma v has some velocity dependence.
But in this case, it doesn't change the order of magnitude.
No, it won't change.
So it will be like very slightly difference.
Just on the velocity.
Just in the velocity.
But there is the other uncertainty, which is related to the dark matter density in those astrophysical objects. But we're gonna cover that later. Okay, so let's continue. So let me rewrite the center of mass energy, or the nth variable, monotone variable, as this one. So I'm gonna pick up from this equation right here. This one. So I have S is equal to P1 plus P2 squared, and then I squared this. Here it is. That's what I have. What I do is, from this equation, what I have is energy is m chi. This energy is m chi. So I get 4m chi, okay, squared, but 2 P1 dot P2. Well, look at this. So I'm assuming they are in the center of mass, okay? But I'm now considering their velocity. Let's say they have some random velocity. Okay? Now I want to take into account the velocity. Why? Because today is slow moving, okay, 0. So that's why we had just 4m chi. But in the early universe, the velocity could be very different. That's why I want to take into account the velocity. Okay? And I'm in the center of mass. So P1 is minus P2. So this minus will get this, with this minus will give me a plus. So I got 2 P1 P2 in module. And then this, what is momentum, is mv. So I get mv squared v squared. Okay? And now I'm gonna do an average. So the dark matter parts do not have a velocity, they have an average velocity. So what I do, I'm gonna average these, I'm gonna average these S here to get an average v squared. V is a velocity, is a Maxwell-Boltzmann distribution. If you assume a velocity dependence, so that's what I'm computing, integrating from minus infinity to infinity, all possible velocities. I plug in the formula for the Maxwell-Boltzmann distribution. You get that v squared average is 3k t over m. Let's k be equal 1, because I don't like to deal with units. And then V squared average is simply 3T temperature over the mass. Okay? Now I plug in this value over here, back here. So I got, from here you can see this side will get 2m squared times v squared. Average of v squared is 3t over m. This m cuts with this m, so I get 6mt, which is exactly what you find here. So now we found what is the center of mass energy for an expanding universe that evolves with temperature. So if there is at 0 temperature, so at colliders, which don't care about expanding universe, what you have is the center of mass energy is just 2m chi, which is the square root of s. Right? Center of mass energy is the square root of s. However, because the universe is expanding, and these particles, they do have a Maxwell-Boltzmann distribution, you have a 6m chi T temperature dependence. So very early, in the very early universe, the dark matter particles had way more energy than they would have today. Okay? And you have to take that into account when you do solve the Boltzmann equation. So let's pick one value just to see it. So just to finish this remark, I have the mass of an electron is half MeV. Mass of a positron, half MeV, obviously. So let's say the mass of the dark matter particle is, instead of being half MeV, is 0.4 MeV. This annihilation today is prohibited. I do not have enough energy to annihilate into a plus and minus, because it's 0.4. Plus and minus is 0.5, 0.5. In the early universe, I could have that energy to annihilate into a plus and minus. So when I do compute the relic density, I have to take into account when that annihilation took place, not today. So as you see, just from this argument alone, the annihilation cross-section is different from today and from back then. Can be very different, okay? For very heavy dark matter particles, it won't change much because I can annihilate anyways, okay? So let's just consider this on a model spectrum. The largest particle we have is the top bottom, okay? 170 GeV, 170 GeV. If dark matter particle is much heavier than 170 GeV, I don't care if it's early universe or today, you annihilate into all of them, all the matter particles, right? Through a Z boson, all of them. Remember my case was chi-chi bar, Z boson, something. Z boson couples to neutrinos, quarks, charged leptons, everything. So you can annihilate into all of them, right? But in the early universe, the same. It won't change in this case, right? Because you can annihilate into all of them. However, if dark matter is lighter than 170 GeV, then it can be different. Because in some cases, some annihilations, you have to sum. Remember the amplitude? You have to take into account each Feynman diagram. For today, there are some diagrams that will be happening. The early universe, there'll be more Feynman diagrams that you have to include. Make sense? So the sigma V there can be very different from the sigma V today. Consequently, the sigma V, or the abundance you get, can be very different if you just use sigma V today and the sigma V back then. Okay? Fine. But let's continue. So, okay, we concluded. And why I said this is an approximation? Well, it's an approximation because I assumed that the dark matter does follow precisely a Maxwell-Boltzmann distribution, which is not precisely correct. Okay, it's an assumption. Okay? According to simulations, it's roughly the same. There are some caveats to that, but I'm going to cover in a different lecture.
So now the T is over the mass there.
Sorry, there's a typo.
Okay.
Thanks, Jacinto. Why is not? So what? So let's now dive into particle physics. So let's do the following. Look at this diagram and go slowly. So I have a two dark matter particles, chi bar, annihilating through a Z, going to Fermi and anti-Fermi. So for collider, the Z pole will happen when the Z mass is twice the dark matter mass, period. This will not change. However, let's say the dark matter velocity is just 1. I picked one value, okay? And let's pick a temperature at the universe. Let's say the universe had some temperature. I fixed the temperature. In a given moment of the time, the history of the universe had a temperature, this temperature. I picked that temperature value. If that temperature is very large, then the pole had happened already. Even if the dark matter particle is lighter than the Z, twice the dark matter particle is smaller than the Z mass. Let's understand this. So the Z pole, the Z mass is 90 GeV. So when the dark matter particle is 45 GeV, there is a pole at the LHC, the Large Hadron Collider. In the early universe, when the dark matter particle was 40 GeV, because of the S, which is the function that enters in the cross-section, S is not just twice the dark matter particle mass, as S plus some function of temperature. When I sum that function of temperature, it can reach the 45 that I want, and that is a pole. You see, Patricia? So the pole for the early universe happens before than the pole that we have today at colliders. Make sense? Fine. So that's the figure. Sigma V in the y-axis and dark matter mass in the x-axis. In the black curve, you see the collider resonance. In the early universe, that would be sort of the resonance that what you would see in the early universe. However, it's not just one point, because the universe is the temperature is decreasing over time. So that pole is changing over time. At some point, they will coincide, right? When the temperature dependence is negligible. It doesn't have to be today. It only matters that the 4m chi here is larger than 6m chi temperature. When that moment happens, then the temperature dependence is irrelevant, and the two poles should coincide. Okay? So why this is an exception to the relic density? Again, because when you compute the relic density, look at this. So when you compute the relic density, the resonance is an exception because of the following. Let's say I pick the mass for the dark matter particle. It's this one, 45 GeV. At 45 GeV, then at different points throughout the history of the universe, the cross-section changed by orders of magnitude. Just because the temperature was decreasing and the pole was moving around. So the sigma V was moving, and also the abundance was moving. Okay? So despite having the same mass, I can have the very different abundances for the dark matter particle. Because the sigma V changes over time or over temperature. Okay? So why is an exception? This exception in the same case, you're going to see it right now below. So what again? So look at this. Let's think of a model. Okay, that will become more clear. Remember, I have chi bar annihilating through a Z boson, Fermi anti-Fermi. The Z boson mass in the standard model, for those who have seen standard model physics course, is G being the SU2 gauge coupling, V is the value of the standard model, 246 GeV, 45, and Z is the Z mass. And chi is the dark matter mass. Now let's think of the following. So the dark matter abundance continues to be like this. Let's say remember, the dark matter abundance is proportional to 1 over sigma V, okay? So let's say, look at the following. I have the dark, I'm varying the dark matter mass, okay? I'm increasing as I go to the right. As I go to the right, I'm increasing the dark matter mass. The Z mass is 90 GeV. And I'm here at 30 GeV. As I increase the sigma V, which is that as I increase the sigma V, as I increase the mass, I increase sigma V. Why? Because the heavier the dark matter particle is, the more channels I can annihilate into. Okay? If a dark matter particle was light, I could annihilate into plus and minus. I increase something, annihilate into mu plus mu minus. Increase even more, tau plus tau minus. Even more, BB bar, and so on. Charm, BB bar, top. The more I increase the dark matter particle mass, the more the channels I can annihilate into. So the larger is the sigma V. So I'm increasing. So I'm right here. I'm right here. Then I'm increasing the dark matter mass towards the right. So as I'm increasing sigma V, omega h squared decreases. But okay, it will decrease slowly. But at some point, I match the pole. So the dark matter particle becomes 45 GeV, or nearly 45. It doesn't have to be 45, because in the early universe, it could be 40. You already reached the pole. Okay? So reach 40, 42 or something, that is a pole. And then the cross-section increases by orders of magnitude proportional to the width of the Z boson. And then the sigma V has a spike. Therefore, the omega, which is inversely proportional, has a dip. So falls. And then I increase the dark matter mass a bit. Increase a bit, I'm outside the pole. Okay? So I'm increasing dark matter mass. So this is driven by the pole only. And then again, it's like I'm outside the resonance. Then I start from the very beginning again. So as I increase the dark matter mass, the omega h squared starts decreasing again. Okay? So this whole region here that I highlighted with not a circle, but this region here is driven by the pole. Everything else is just using this formula. Okay? So fine. So the pole drives an exception in the relic density curve. Instead of just being smoothly decreasing with the dark matter mass, there's a dip. Okay? So the cross section you need to get the right relic density can be orders of magnitude different when you are at the pole or near the resonance. Okay? So let's say I need 3 × 10⁻26 centimeter cube per second for sigma V to get the right relic density, but not at the resonance. At the resonance could be very orders of magnitude different. Okay? Make sense? Awesome. Okay, so that's what I'm saying. And let's now go to, since there are many people working on indirect dark matter detection, I'm going to apply this scenario to indirect dark matter detection. So look at this. So I have a limit. So the guys from São Carlos there work a lot, work really hard, and get a limit from CTA, which is the one in blue. And say, hey, for now, we use CTA data, and we excluded the sigma V, and the sigma V should be below some value. So everything above this blue curve is excluded using CTA. So you cannot have annihilation cross-section, not average. Annihilation cross-section is different from thermal annihilation cross-section. Annihilation cross-section should be smaller than that curve. Everything above will be excluded. Okay? Fine. And just to remind you really fast, why this happens, because the flux of gamma rays is proportional to sigma V. So the larger the annihilation cross-section, the larger the flux. But I did not see lots of flux of gamma rays. So this cross-section should be smaller than some value. Okay? So sigma V is 10, gives me 10 flux, 10 whatever units of gamma rays. But then I did not see the 10. I saw something below 10. So sigma V should be below whatever. Fine. And the shape of the curve that I'm going to cover this later has to do with the fact that the flux is sigma v over m chi-squared. But okay, look at this. So I have to be below. Then I look at this plot and say, if the dark matter, if I keep the same annihilation cross-section, let's draw a black line here. That's the sigma v for my model, okay? My model. My model predicts a sigma v of some value. This point here, whatever it is. And then what CTA say, hey, in your model, the dark matter particle should be larger than 50 GeV. Because if it's smaller than 50 GeV, I exclude, right? Because it will be above the curve. Above the curve is excluded. I have to be below the blue curve. So it's excluded. So I have to be below. Therefore, I have to increase the dark matter mass to be beyond 50 GeV to be okay, consistent with gamma ray data. However, sigma v is different from thermal average, as we've seen. So now look at this. I'm going to consider a very simple model, no velocity dependence, nothing. I'm just saying that the dark matter annihilation cross-section, there's no velocity dependence, nothing else. Just sigma v depends on A. Fine. If that's true, we just saw it. And now look at this. Look at this plot. We just saw it. The collider is the one in black. In the early universe, there will be the curve in blue, shifted towards the left, right? Because the resonance will happen for lighter dark matter masses, right? I don't need to be at 45 GeV. I need to be at 40 something. The resonance will occur because of the contribution from the temperature, right? Fine. So now look at this plot again. This is the same plot I showed you before. This is the same one, okay? I'm gonna go back here. And let's say that's the CTA bound, the one in red. CTA is covering, killing everything. And this curve in blue is the one that gives me the correct relic density, h squared equal 0.1, okay? I'm just assuming. If you see this curve, saying, look, Fernando, if the whole regional parameter space that gives the correct relic density is the one in black, what's saying CTA is saying that, okay, you can be here, and you can also be there, but this region is excluded, the one in the middle, okay? Because it's giving you a cross-section sigma v, which is too large, and CTA, we excluded everything above the curve. Okay, fine. However, the sigma v is different from thermal sigma v, and the thermal sigma v that actually gives me the correct relic density is not the one in black. The one that gives me correct relic density is the one in blue. And the one in blue looks like this one. It's shifted towards the left. Okay? I shifted the black one towards the left to be the blue one. Look at the blue one. The blue one is the curve that gives me the correct relic density. And CTA is excluding everything above. CTA is still the same limit. I just overlaid the one in blue. It's like this one. I'm here. So let me do there. So now I'm going to do a curve, which is this one. But now I pick, for this range of masses, look, CTA is saying that this range of mass is excluded, right? I cannot be there. CTA said, okay, this range of mass is not possible. Okay, fine? It's not possible. However, the one that gives me the correct relic density is not this one. It's this one. Now I'll tell you. Now you tell me, is this mass okay or not? It is. This mass is below the red curve. See? So when you place a bound on sigma v, that sigma v, okay, it's fine, it's a bound. But that does not prohibit my model from giving me the correct relic density. Because that bound, we excluded the thermal cross-section, which is the cross-section that gives me the correct relic density. No. Because the thermal cross-section is different from sigma V. Sigma V being 3 × 10⁻26 is not the same as thermal sigma V being 3 × 10⁻26. Because they are shifted towards the left because of the contribution from the temperature. Okay? So let me just finish. Ricardo has a question.
Oh, I would just say that the prohibited region is shifted as well. So the models that could be in those regions are doesn't.
Yeah, so I just plotted a bump on purpose, okay? To make sure, for instance, this region here is not excluded by CTA, but does not, and this gives me the correct relic density. I'm just assuming that the whole curve gives me correct. This is not true, okay? I'm just an assumption. In reality, that's not what happens. So you have to change other things besides the mass. I'm just saying that the relic density just depends on the mass and sigma V and nothing else. If that's only sigma V and mass gives me the correct relic density, that's it. So I can pick values of sigma V and cross-section that gives me the correct relic density. And I'm assuming to be the whole curve in black or the whole curve in blue. So when they say we exclude the thermal cross-section, when they say thermal cross-section is not thermal, what CTA does, Fermilat did, they did not exclude the thermal cross-section. The thermal cross-section is different from sigma V in many cases. In some cases, yes, they can coincide. In many other cases, they do not coincide. I just show you one when there is a resonance. When there is a resonance, this resonance shifts the curve where the relic density gives the correct value. So for a given mass, the same, for instance, I pick a mass, dark matter mass, 45 GeV. There's a pole right here, 45 GeV. It's a collider. The pole for dark matter 45 GeV is here, right? For the Z boson, this is 45. And then you say, hey, if this is the curve that gives me the correct relic density, omega h squared equal 0.1, the pole is excluded for dark matter masses of 45 GeV. No, no, no. The pole for thermal cross-section happens before. So that 45 GeV is actually consistent to give me the correct relic density, and you do not exclude it. No, but I exclude. No, you do not. Because the sigma V is below the curve. And that's, do you think it's easy to convince experimentalists that's correct? It's for now, I'm seeing the curve. See, it's above the curve. I know it's above the curve. But the thermal, this one is okay. You're right. But then if I put this, your conclusion is not correct. For sigma V, yes, their limit is fine. But that's not what I care about. What I care about for dark matter is this one, right? And that one is the blue curve.
And this data is from today.
Hmm?
So
yes,
from today.
today.
So it's only relevant for the black curve.
Yes, for the black curve, which is now tied to the relic density. Sure, everything excluded above the red line, yes, it's excluded. For sigma V, not for average cross-section. For sigma V, fine. Is excluded for now? Yes, it's excluded. But not for the corresponding relic density. It's different. Okay? Any questions? Everybody's quiet. So this is what I was just discussing, that this region here would be okay. And now I'm discussing again. So what I want to conclude is that CTA, so for instance, if this is true, CTA would not exclude that range of mass. Okay? Would not. See?
Yes, it does not exclude the abundance in the water. Curve itself. What information do I get from the black curve itself? Like what information do I get?
So the correct is, if by any chance in a given model, particle physics model, sigma V happens to be precisely the thermal sigma V, then everything above the red curve in your model is excluded. Period. There's a if in the beginning. Okay? So this is not a general conclusion as is reported in the papers. Listen, we exclude the thermal cross-section. No, you do not exclude the thermal cross-section. You exclude sigma V, not thermal. You can read in the papers from collaboration, 200 and something people. We exclude the thermal cross-section for dark matter. But this is not true.
But have you gained any information whatsoever?
No, they gain information on sigma V. There are models as well that sigma V is equal to thermal sigma V. For those models, this conclusion holds. For those models, not for all of them. So when you say, we exclude the thermal cross-section, this statement is wrong. You say, in models which, this is a scientific paper, right? So you're not giving a talk to students where you want to be really precise. So in a scientific paper, you say, the correct statement would be, for models at which the thermal cross-section coincides with the sigma V today, models where the range of masses is blah, 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 is excluded. Do not give you the correct relic density. Or you can just say, we exclude sigma V below this mass. That's it. You don't need to include the thermal. This word thermal in it. That's it. You can say, if you see a limit, which is this one I showed you in the beginning, let's say this one here, you can say, so using CTA data, we excluded sigma V below 50 GeV. That's fully correct. What you're saying is nothing wrong. This does not mean that you excluded all dark matter models for masses below 50 GeV. You see the difference? You exclude sigma V below 50 GeV. Does not mean that all dark matter models with masses below 50 GeV are excluded. Because in many of them, I can tune my model for the resonance to occur right there. Okay?
It seems like the real point is if we detect some particle which is very close, which is very similar to dark matter, we could exclude a lot of models.
Yeah, and the reason why I'm saying this is because at the end of the day, you don't want to use just one data set. Yes. You have to combine with other sources, which are very independent from this one. And then when you don't see a signal, you exclude this limit, this regional parameter space, and then you use a different orthogonal data set to exclude a different regional parameter space, then you say, look, this thing is really excluded because even if you move from the pole, thermal effects, I don't care, this whole parameter space is excluded. But this will be covered at the end of the course when we talk about dark matter complementarity. So the second effect is threshold effect. So I'm afraid that I won't cover everything. So I'll go faster now. So this one is basically trivial in this sense, much trivial than the other one. Threshold effects. So let's say I have dark matter, like chi bar, annihilating to plus or minus, or mu plus mu minus. As we've seen, at zero temperature, if dark matter is lighter than the electron, dark matter cannot annihilate into plus or minus, right? It cannot. This annihilation is prohibited. At early times, it is possible. Well, it depends on dark matter mass, right? Because the contribution from temperature is 6 times m dark matter times temperature. So you have to add at some temperature. Yes, temperature is infinite. Yeah, sure, it will be always possible. But that's not what happens. So what matters for us is if this is happening at freeze-out time. At freeze-out time, I know the temperature because the temperature is X is m chi over T. So T is m chi over X. And X is roughly 20, 30, whatever. Okay? So you get this value, the freeze-out, from solving the fully Boltzmann equations. And it's impossible to do it analytically. Okay? So just remember that when we show the plot, just doing some defining the number density, we picked different models and found that X, the crossing will happen between 20, 40 or something. So when you do it something in a proper way, you find that's also the same. The conclusion still holds. And it's still around, it's not even 40, it's around 20 and 30, no more than 30. So it should be around that. So let's pick a 20. So m chi over 20. So therefore, the temperature is proportional to the dark matter mass. So there is a limit at which you can get some temperature correction to the center of mass energy. Okay? Understood? Got it? Yeah. Okay. All right. Why is it not going down? It froze? It froze? It froze. Oh no, come on. Okay. Oops. Okay. So what I'm showing here is just that this center of mass energy or square root of the center of mass energy grows with the temperature, right? So according to this relation. Okay, obeying this relation. Fine. So now let's pick an example to be clear. Let's say the dark matter particle mass is 88 GeV. So I have 88 GeV here. 88 GeV. It's not 88. This should be smaller. Should be actually not 88. So there's a typo here. So I made a mistake in my math. I made a stupid mistake. So I want to pick was 48 because I want what 48 is likely before 45 actually 43 GeV. Let me erase this. So I'm assuming that m chi is 43 GeV. Okay. So I'm not at the resonance, at the Z resonance, right? I'm not. Fine. Let me cover something else. Hold on. Leave it at 88. My argument will still hold. 88 GeV. The resonance topic I already covered. 88 GeV. Sorry, let me take that back. 88. The Z mass is 90. Remember? 90 GeV. So this process happens? Happens, sure. I can annihilate into all these fermions, right? B is 4, GeV, S is 200. C is nearly 1 GeV, D is 4 MeV, U is 2 MeV, tau is 1.7, 100 MeV, and half MeV. So I can annihilate into all of them, right? I have enough rest energy to annihilate into all of them. So the annihilation, this annihilation here, that's the one that I want to emphasize. Chi bar go into ZZ does not happen. Agree with me? The Z boson is 90 GeV. Yeah. This process does not happen today. Right. Does not happen today, right? Okay. Just by forming GeV. Okay. It does not happen today. Look at this. Look how interesting it is. The contribution of the... So let's say, yes. So let's say that I can annihilate into all charged fermions, okay? Which all these fermions here are charged, right? Electric charge. So when I do compute the amount of gamma rays, for instance, that dark matter produces, I have to account for all possible annihilation channels and hadronize and get all gamma rays they produce. In the early universe, the temperature function could give me 2 GeV to have enough mass of center of mass energy to annihilate into ZZ, right? ZZ bosons, pairs. Okay, and this one is the middle sky. Okay, because if this vertex happens, this one also happens, and this one also happens. It's the same. This vertex here is exactly this one. Okay, and just opening up the diagram. Okay, so now picking the value I chose, chi bar ZZ. So XF is m chi over 20 over T, which is X should be around 20. Okay, so that's the exercise I did. So the temperature at which the freeze-out happens is m chi over 20. I took m chi was 88 GeV here. I put 88 divided by 20, gives me 4.4 GeV. Therefore, the square root of S would be changed by m chi squared, 6 times m chi times 4.4 GV. I'll put the 4 just to approximate. So it gives me 181. So look, I need 90 GV here and 90 GV there, right? So I need 180. But because of the early universe, I get 181. So I can annihilate into pairs of Z bosons in the early universe, but not today. So the sigma V today for our 88 GV fermion, dark matter fermion, is different from this average sigma V in the early universe. So the fact that, for instance, one was annihilation, right? So happening the annihilation. The other one is saying whether I should include or not a final state in my calculation, depending on the temperature at which that annihilation took place, is called threshold effect.
Oh,
So you are with a mass which is close to the final state mass, but it's not enough to annihilate into the final state. But because of the temperature contribution, gives you the enough to annihilate. So this gets a threshold. But remember, as the more channels I include, the larger is the sigma V. So once I did not have the Z boson, I had one sigma V. With temperature effect, you include a Z boson, then the sigma V gets larger. Okay? So let's say now my model is this one. Dark matter annihilating through a Z boson coupling to all certain monofermions. That's my model. And then, look at this. Today, I measure one sigma V. Sigma V is smaller than the sigma V I use to compute the right relic density. Because the sigma V for the relic density had the ZZ final state included, but the sigma V today doesn't.
yes. It makes sense in terms
See,
of
so I can, for instance, you say, but I'm excluding the thermal sigma V. No, you're not excluding the thermal sigma V. The sigma V today can be smaller than the sigma V for the relic density. See, can be smaller. Through resonance, through threshold, can be smaller. For the resonance, the same. Look, remember, the blue curve is smaller at a given point for mass. So resonance effects and threshold effects can make the sigma V today be different from the sigma V back then. Okay, so they go in both directions. So this resonance saying is smaller there, and today is larger. The threshold is the opposite. Because the threshold is making, once I include the ZZ, there was large, and today there is no ZZ final state, so it's smaller. So depending on the effects you might have, the final message is the sigma V today can be very different from the sigma V in the early universe. This thermal sigma V. Okay? One, you can increase or you can decrease. Depends on your model.
What kind of model would have this kind of threshold?
There's a question there. Could you?
Yes, Professor, so just to make things clear, in both cases, you can have, for instance, a velocity-independent cross-section, let's say, but the question is, in the same case, we will have processes that are now kinetically open. So
Exactly.
even sigma does not depend on V. Now, a new process, do it to a resonance or do it like thermal channel is open. So even
Yes.
in a
Even in this case.
even a S-wave expansion, for instance.
Yes, exactly.
Okay.
So if I go to a P wave, then it's very, very different. Because my sigma V depends on the velocity, then it's obvious, right? In the early universe, the velocity was large, and today is small. So obviously sigma V today is very small. So it's easy for me to get the right relic density. Let's say that I need the relic density of 3 × 10⁻²⁴. Current data exclude 10⁻²⁶, so 2 orders of magnitude stronger. But I can have a thermal cross-section of 3 × 10⁻²⁴. If this is velocity dependent. Because then today the velocity is basically 0. I get these 3 orders of magnitude, 2 orders of magnitude easily out of my result. Remember, v is 10 to minus 3c. When we square, it's 10 to minus 6. I get 6 orders of magnitude difference just from the velocity. Let's say that in the very early universe, they had lots of energy. V was roughly c. Okay? But they were not roughly c because they were slow moving. For the cold relic, they were slow moving still. Okay? They're non-relativistic. They are non-relativistic. They're still non-relativistic. It's not the same velocity, but they're still non-relativistic.
So then you can always use this argument if you have a model that has
velocity dependence.
I mean, if you have a model that has strong interactions, you can always say, well, my model has a velocity difference, then
So strongly interacting massive particles were not excluded because of indirect detection arguments. Were not. As long as you included some velocity dependent in it. Okay? We're not. We're excluded by something else. Is that if you concentrate dark matter in the center of celestial bodies, such as the sun, they overheat the sun, and then you have measurements of the temperature of the sun, and that's how you excluded the presence of strong interacting massive particles. Okay, so you understood this part, right? So we could have, as he said it, correct? If it's velocity dependent, then it's easy to justify. But I'm saying even the simplest scenario, there is no velocity dependence whatsoever. I can still make them different. Okay? I can still make them different. So who's going to say, oh, for now, but you cannot choose this dark matter mass? I choose whatever I want. I built them my model, right? As long as it's consistent with data, that's fine. I cannot make it like some very complicated model. No, I'm just tuning masses here, right? That's all I'm doing. Not saying, this sigma, there is some new symmetry, whatever I come. No, I'm just tuning masses. That's all. Otherwise, someone has to explain me why the electron has a half MeV mass. If somebody has an explanation for that, then maybe can convince me that I need to really pick what dark matter mass should be. We don't know. Data is data, so we need to obey the data. That we cannot run from that. Besides that, it's fine. Okay, fine. So this will not change, but it will change sigma v, as I told you before. Now let's go another one because I need to leave. I'm not gonna cover this another example I wrote. So I wrote a different example and computed the change in the abundance when you do have and do not have these other channels. Okay, I did another case. I did for the ZZ final state, right? Now I did another one explicitly for dark matter going to 5, 5 being a Higgs or a new scalar, whatever. So this argument is the same. So I just want to finish because I have almost no time. So co-annihilation. Co-annihilation is the following, is very similar. So you have chi going to fermi. Chi1 here, guys, is not necessarily the dark matter particle. Chi1 and Chi2 are not necessarily the dark matter particle. What I'm trying to say is the following. So instead of showing these formulas, I'm going to explain to you everything in one plot. So this is the X, that's the yield for the dark matter mass, for dark matter particle. And here it is. This is the plot. It goes like this in equilibrium, right? Okay. But dark matter froze out. Stayed something. And gives me the correct sigma v. Let's say it gives me the correct relic density. I'm just assuming whatever that freeze out is. Whatever the mass is, whatever. I'm just doing in general. Let's say I have this plot and gives me the correct relic density. However, I have in my model other particles which are also weakly interactive massive particles, but they are not stable. They are not stable. Okay? That's the only difference. They have the same roughly coupling. The mass could be roughly the same, but they are not stable for some reason, from some symmetry arguments or whatever. If they are stable, if they're not stable, they have roughly the same mass, roughly the same interactions, they'll follow a curve very similar to this one, the one in black. Okay? Very similar. And then they also decouple. Okay? I'm not, could be right on top of the blue one, but I'm just putting it different. So that's my co-annihilating particle. But it's not stable. So it froze out when the interaction rate equals the expansion rate, but it froze out. But that particle is no longer stable. It's not stable. It could be decaying, what I'm saying, comparing the expansion rate, the interaction rate, or decay rate with the expansion rate. It decoupled, but it's not stable. So it will decay. Decay to what? To the lightest stable particle that is, which happens to be dark matter. So that particle decayed, and then decayed into what? Contributing to the blue one, which is the dark matter. So I have a particle chi1 existed there, was produced with some abundance. You're going to see the importance of this soon enough. Hold on. Let's say that this value here is h squared equal 0.009. So it's not 0.1, it's 0.009. But there is a co-annihilating particle. There's another particle that's very similar to the dark matter particle. It's neutral, has mass, weak interactions, but it's not stable. It happens a lot. It happens in many models. Supersymmetry, extra dimensions, left-right models, and so on. But it produces. But then it decays. When it decays, guys, will contribute to the abundance of the dark matter particle. So the dark matter particle abundance was, when it was produced, was here, 0.09. So it's not enough to be the 0.1. But then some other particle, which was also thermally produced, decayed. And that abundance decayed into that one. So when it decays, now you have to sum what you had in blue with the one you had from the decaying of the other particle. Okay? And if you remember, if that particle froze out here in red, its abundance is very large because it's a yield very large. So if it froze out here, the overall abundance of dark matter will be the one in blue plus the one in red, but this one in red will disappear, right? You become just blue because it's just dark matter particle. There is no red anymore. Okay? We could do dry in red. So in red will be the sum of the blue and the red. This gap here is very large. Could be order of magnitude different. What I'm trying to say is, I produce some dark matter particle which is not 0.01, 0.1. Is the abundance at the end of the day I compute is 0.09. I do not have enough. But then in my model, there's another particle which has similar interactions, and then it froze out and then decays. Let's say it's 0.09, but this similar dark matter particle froze out later. Let's say it froze out later. It froze out later means that it has a larger sigma v, because the larger the sigma v, the more in equilibrium they stay, right? The more time they stay in equilibrium. So it has a larger sigma v. If it has a larger sigma v, it has a smaller abundance. And that abundance is precisely 0.001. Okay? So the one annihilates later. This one stays annihilated later, and this abundance here is 0.001. It froze out, and then it's there. But then it decays into dark matter. So the overall dark matter abundance is the one from the freeze out, solving the Boltzmann equation, plus the amount of all the particle I had, because the same amount of particle will not. So the same amount I had of a new particle will be the same amount of dark matter particles I have. I just sum. This 0.09 with the plus 0.1 gives me the 0.1 that I needed in the first place. So a way to get the right relative density. So I have a sigma v, the one in blue. Pay attention. If I got an omega h squared of 0.09, means that the sigma v I had was large, right? Because omega is 1 over sigma v. I did not get the right relative density because sigma v was large, right? I need a bit smaller sigma v to get more abundance, right? The more I stay in equilibrium, the less I have. So it produces, I have a larger sigma v, but still I get the right relic density, because it doesn't come just from this one, it comes also from the decay of other particles. So decaying of the other particles or decaying of co-annihilating particles contribute as a new way to make sure that that rule, omega h squared 1 or sigma has to be 3 × 10⁻26 is wrong, is broken. This rule is broken because I can have a different value for sigma v average and still get the overall relic density right, because that other extra came from something else. Okay? Got it. I have time for one question and then I have to leave.
I think there is a caveat in this case, because the later the particle decouples from the thermal equilibrium, the smaller the mass.
The mass.
So in this case, for example, a dark matter particle would be maybe, if it decouples earlier than this particle, it would be large. It would have a large mass than this particle. So
there should be a mass split in between the two particles.
Yeah. So yeah, something like
I'm gonna
like
cover
this,
that in the next lecture.
Okay. Or other channels, like these particles would interact with also the standard model, I don't know, and then it would produce a very small fraction of thermal particles in order to avoid CMB being bound. But
no, this everything happened way before.
Yes, I know, but for example, if I produce a lot of SM particles and then radiation, maybe,
this happened way before.
But I mean, just it. I would have more terms in my decay rate. So I would have the term like that one for the Z prime photon, that photon, for example. So I would have a term for dark matter decay. In the two neutrinos, the two right-hand neutrinos, the heaviest ones, they would decay into the lightest one, which would be dark matter, and also in the standard model further.
I know, but in this case, is that it decouples much later. They are roughly happening roughly at the same time.
It would have to be a scalar.
So it doesn't matter if it's a scalar. I'm just saying these co-annihilation is when the freeze-out temperature of those two particles are roughly the same. They have roughly the same annihilation cross-section. It's not like they froze out and then they are long-lived and then they decay. No, I'm not considering them to be long-lived and then they decay, because it's out of equilibrium contribution. This one was equilibrium and then they eventually decayed, but they were in thermal equilibrium. Then they can be short-lived.
Yes.
They were in thermal equilibrium and then eventually they decay. As soon as they depart from equilibrium, then they decay. And then that decay will contribute to dark matter bonds, which is roughly at the same time when the freeze-out happened. So you get an exhibition just out of that. So when it happens for models where dark matter has co-annihilating particles in a doublet, because doublets, all the fields in the doublet have to share the same interactions like the standard model. Very similar, and so this happens for particular cases. Okay, it's not really common to have co-annihilation. No, it's not common to have co-annihilation. Well, in very complicated models such as SUSY, then you can have. Okay, but I need to finish, then we can pick up from this in the next lecture. Okay, the next lecture. Sorry, I'm gonna stop recording. And I hope everybody can ask questions.